Hi, let's delve into the exciting concept of differentiability. I'm going to show it to you on the most basic level and then show it to you also applied to a few tedious examples. Basically, you can think of it as this. This curve is differentiable because at any point along the way, I can find a slope of that curve. I might need some calculus and some derivative knowledge, but everywhere I am on that curve, I could use a tangent line to estimate the slope of that curve, so that curve is said to be differentiable. This curve right here is not differentiable, and it's all because of this one spot right there. We have a discontinuous spot, but now I have entered this little detail black hole that says at that spot, I can't find a slope because that spot's not there. So you can't say that you can find a slope for every point in this domain because you can't at that spot, so it's non-differentiable. Let's look at this one right here. This is non-differentiable. If I look at all of these points along here, I can find slopes, and all of these points along here, I can find slopes. But the problem is, right there, I cannot find a slope. There is not a tangent line that can be drawn to that spot that is definitively going to give me that slope. Here's why. Some people would say, well, I could draw a tangent line like that. True, because that line hits that spot in only one location, so it's kind of like a tangent line. But someone else could say, well, I could draw a line that looks like that only hits it in one location. And then another joker could say, well, I could draw a line like that hits it only in one location. So you would have at least three people, possibly an infinite number of people, arguing that their tangent line represents the slope at that spot. So the point is this. If you have a corner point, that is non-differentiable. The true calculus behind that is something we're going to talk about here in a moment, but just for right now, corner point, non-differentiable. And I put two other graphs here. These are also both non-differentiable simply because they are not continuous. So discontinuous, non-differentiable. Discontinuous, non-differentiable. Corner point, non-differentiable. I can find a tangent line or a slope anywhere in the domain, differentiable. So now we'll get into a little bit of the nitty-gritty. This is a non-differentiable point because it's a corner point, but the real calculus behind that is this. The left-hand slope, and we'll call that the left-hand derivative, does not equal the right-hand derivative. In this case, at x equals, I don't know what x value that is, so who knows. But a corner point, if you want to get very analytical about it, has this phenomenon that just to the left of that point, my slope might be, say, positive 2. So I could say left-hand derivative equals positive 2. And then just to the right of that point, my right-hand slope, or my right-hand derivative, is negative. I'll just say that looks like negative 1 1/2. Because my left-hand derivative does not equal the right-hand derivative, it is a non-differentiable point. That's the calculus rule, although your eyeballs can say corner point, non-differentiable. Don't mix up left-hand derivative and right-hand derivative with left-hand limit and right-hand limit. They are very different things. So if I had to summarize this, I would say if it's discontinuous, it is not differentiable. If it is continuous, I just have to look and make sure, is there ever a spot where the left-hand derivative and the right-hand derivative are not equal? There is this thing that I've kind of sort of made up called the ABCD rule. and it's just a little nifty way to help you remember some things. You might think this means always boring continuous differentiable, but I don't know what the A and B stand for, but I know the C stands for continuous and the D stands for differentiable. And it kind of goes like this. If a function isn't continuous, then it can't be differentiable. You can't get to D if you can't say yes to C. And there's another thing that comes from this. If a function is differentiable, then it must be continuous. So if I got to D, I must have already been through C. So these two statements, along with the ABCD rule, can kind of help you remember some of the stuff we did back here. And this shows up on an AP test. Let me arrange this a little bit. All right. So I made up a fake start to an AP question, but this happens a lot. The question might say, function g of x is differentiable, blah, 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 because they're going to go on and tell me more things about g of x, but we don't care. As soon as I see that they tell me g of x is differentiable, then I know for the rest of the problem, I can assume that g of x must be a continuous function because of the ABCD rule. And so if I had to write something relating to continuity, I would say because g of x is stated to be differentiable, then it is also known to be continuous. I'm going to give you a couple of ways that this might be applied, but this concept could show up in many different ways. I'm taking a piecewise function, so automatically you're a little bit angry, perhaps intimidated. Is this function differentiable? Well, there's a couple of different ways you can go about this. The first way, which I've already done, is I can graph this thing. X equals 0 is my border, and to the left of x equals 0, I have this linear function. To the right of x equals 0, I have this parabola. Well, they meet up at exactly x equals 1. That's nice. You can check it out by plugging in some numbers. So I know by the ABCD rule that we have said yes to continuity. So now I would have to determine, is the slope just to the left of that spot the same as the slope just to the right? You could trust your eyeballs, but that's not a good idea because this is math and so we have to be exact. So the other thing you could do is you could actually take the derivative of that piecewise function. By the power rule, and I hope by the time you're watching this you've learned the power rule, the derivative of this is -2. This, by the way, is x squared minus 2x plus 1, so that derivative is 2x minus 2. And the point that I was worried about was x equals 0. So if I plug an x equals 0 into here, there's nothing to plug into here, so that's a -2 to the left, because that was the left side function. This is the right side function. I plug an x equals 0 into here, and I also get a -2. So what I'm saying there is, if I'm worried about the slope right at x equals 0, I can plug it into the left side and the right side, and I end up with the same answer in both cases. So I can say the left-hand derivative does equal the right-hand derivative at x equals 0. So it is a differentiable function. Now I could change that. For example, if I did this little detail, if I took out this equal sign and made that an open circle, then you don't have anything else to do because you already know that it's not continuous. You would have said no to continuity, so you'd say no to differentiability. I'm going to do one more quick one. Similar piecewise function, but now just by graphing, I can already identify a corner point. So I would say this is non-differentiable. The slang justification is it's a corner point. The better justification is the left-hand derivative does not equal the right-hand derivative at x equals 0. And if I wanted to create a derivative, I would say something like this. The derivative is 3, and then remember this one from the other side was x squared minus 2x plus 1. So that derivative is 2x minus 2. But now we have to put on our math lawyer hat. This is a non-differentiable spot. So I would say this occurs for x from negative infinity less than 0. I cannot include 0 there. And for this, I can say 0. But notice I don't include 0. My derivative does never include 0 in this case, because that's a non-differentiable point. If I go back to that problem we were working on before, and I didn't do this, so I should do this, the derivative would be negative 2. I'm going to include 0 because we did have a derivative value at 0 when that was filled in. And then over here, if I feel like it, I can include it again. So those are little details that show you how this concept of differentiability, very easy in picture form, can be a little bit more tedious in equation form. That's differentiability for you.